So KDB plus transformation with GPUs. So this is a new initiative at KX. Essentially, the idea here is that can we build a GPU-enabled version of KDB Plus? We have been used to the KDB Plus performance using CPUs, but the idea here is that if we use GPUs, we can significantly speed up some of the most common operations. Now, we know that KDB Plus has been one of the best-in-class databases in the industry, historically. There are high-performance interfaces, and over the years, there have been a number of new innovations such as KDB.ai, KDB-X, PyKX, and so on. And we have kind of maxed out in terms of the CPU utilization, memory utilization. So we've kind of pushed the hardware to the max. So the question that the team asked itself is, what can we do to take KDB Plus to the next level, while keeping it reliable, maintaining system integrity, but and keeping all those facets intact? Can we still take KDB Plus to the next level? So the answer to that, it appears, has been the KDB Plus native GPU library. So it's a Q-native library that offloads KDB Plus operators to NVIDIA GPUs. And what we are observing is 5 to 100x to up to 500x speedups on matrix operations, as of joins, vectorized transformations. One of the core ideas or thinking philosophy behind the KDB Plus native GPU library is that we want to make it easy, embarrassingly easy. Can this library be essentially like a drop-in replacement, a .so file that you take and it just works? We know how complicated it can be to use CUDA libraries, and it does require a fair amount of both programming experience, expertise, as well as infrastructural expertise. So keeping those in mind, the objective here is, can we make the use of GPU library so simple that we can minimize the infrastructure or programming competency overhead? There are some core features of this GPU library that has been very unique. Firstly, there's a seamless KDB plus Q integration. As I mentioned, it's a drop-in replacement for Q primitives. And it's a simple migration. So if we need to move data between the GPU, DRAM, VRAM, then there are simple utilities such as .gpu.toDevice and .gpu.fromDevice for moving data. A number of the table operations have been GPU enabled, such as .gpu.select, essentially. So if you have a select statement, could we just swap out the select for .gpu.select and use the functional form of select in order to run it on the GPU? For as of joins, there's .gpu.aj. For sorting, there's .gpu.xasc. For weighted averages, there's .gpu.vwap and others. In addition, what we're also trying to implement, in fact, it's already been done for some of the primitives, is multi-GPU scaling with Peach. That is, when you issue a command, when you have a certain, if you have a certain KDB plus code that requires, for instance, in CPUs, we would use Speech so that we can parallelize. Our GPU is already parallelized, but the idea here is, can we parallelize across multiple GPU cards? And can we do that again seamlessly using Peach? So that's multi-GPU scaling. And finally, there's GPU Direct for disk to GPU transfers. So that kind of bypasses, some of the latency that's inherent if you don't have tools such as GPU Direct. And uh, what we're observing here is significant speed up, such as 15x faster end of day sort with .gp.xasc, 14x faster select performance with GPU select, and many others, right? Faster TCA calculation, significantly faster linear algebra operations, and so on. So What I would like to do is show some of these examples, but show them in real time. So this is a notebook that we have created that showcases some of the most common use cases that we have seen from requests from our clients. So firstly, I'm going to load all the libraries. This is a very familiar Python notebook. We have some utilities that helps us to plot different charts. We specify 16 slaves, gp.queue, CSV save directory, where we're going to save certain intermediary files. So I'm going to load a sample data set of NASDAQ 100. There's OHLC, adjusted close, volume, dividends, amount, split coefficient, SIM, timestamp, and so on. And we're going to use that for some of our examples. Just to take a step back and see what kind of GPU we are using. This is an NVIDIA A100 with 80 gigs. So I'm going to load in the NASDAQ 100 in queue, and I'm going to simulate 10 million records, right? So I'm going to simulate 10 million records and create a table T. So just to see what that table looks like, these are some sample rows from the table. You have timestamps, price, size, SIM, close. So the use cases that we want to go through, firstly, the end of day sorting. And what that does is the idea here is sorting large end of day tables on GPU instead of on disk. And what that does is that it shortens batch windows and enables more reruns with the same wall clock. The second is .gp.select. What is .gp.select? Is the familiar SQL select statement, QSQL select statement, runs QSQL filters, aggregations, and so on. And essentially what this means is that the code that you have, you can kind of GPU enable it using very familiar syntax that you're used to. Third use case is on VWAP on GPU. We are again going to use .gp.select, use the formula for GPU for VWAP. Then we're going to go into .gp.aj, which is for as of joins, join trades to quotes as of on GPU. And the benefit there is that we can significantly accelerate TCA pipelines, reduce time to insight, slippage, market impact, if we can optimize .gp.aj. There's also an example of custom kernels. So bespoke GPU kernels for vector operations, shifts, and this could significantly speed up essentially proprietary transforms without leaving queue. And finally, a number of matrix operations are already there in the GPU library. The one that I'm going to show here is .gpu.gem, and I'm going to show an example of a vector to a matrix multiplication and how that compares between GPU and CPU. So the first example is end of day sorting. End of day sorting, the example that we have here is to sort 10 million records on disk, in memory, and in GPU. So the function we're going to use is .gpu.xasc, and we're going to move the data with .gpu.table to GPU. So in the first example here, we're going to do the CPU and on disk sorting. So in memory and on disk sorting. So the disk sort for 10 million records took 1.726 seconds. The in-memory sorting took 1.3 seconds. Now we're going to move the data into GPU. And if we notice, we are using .gp.xasc, and it's a very similar syntax to this one. It's the same thing, except now we have .gpu.xasc. So I'm going to run that. That takes 122 milliseconds. If we compare the difference, we have 14x speed up just by into GPU, which is kind of expected, but nevertheless, if we can see, the only change we had to do here was switch from XSC to .gp.xasc, and we have a 14 times speed up. That means the operation, the sorting that you're doing, you can do it in 1/14 of the time. Instead of it taking 1 hour, you could do that in a fraction of the time, like 4 minutes or 5 minutes or something, right? And that's a significant time saving. So observed speed up on this particular data set 12 to 15x, significantly shrinks the end of day window. And essentially from a business perspective, you can do much more frequent reconciliations. You can support larger in universes, histories. That is because the sorting has now become so much faster. You could now think of having larger data, larger vectors to sort, and so there's a significant benefit here. But one of the caveats I suppose to keep in mind is that the GPU memory fit and device to host transfer can dominate for small tables. So it's much better if you plan your sorting strategy accordingly. The next example is .gpu.select. And the idea here is that we're going to run a query, find some volume by sim and algo from 10 million records. So we're going to use .gpu.select. And again, as before, we're going to move the data to GPU using .gpu.table to GPU. We're going to perform a functional select on a foreign GPU table. And if you see number of different data types, primitives are already supported, timestamps, sum, average, min, max, binary operations, and so on. So in this example, we are running it on CPU first. And the CPU time to do that sorting was 1.9 seconds, right? And mind you, this is 50 reruns, right? So we are running this 50 times, and that takes 1.9 seconds. We're going to do the same thing, except this time we're going to use .gpu.select instead of select. As you can see, we are using here the functional form of the same query. Select some size, yeah, and by sim algo from T1. And so we're going to run this, and we're going to run this 50 times and compare the speed, right? So that took 133 milliseconds. So compare this. This took 1,931 seconds. This took 133 milliseconds. If you see the speed up, that was a 14.5x speed up. All we had to do here, again, just like the previous example, was change from select to .gpu.select. And just by doing that simple change, a small change, my time to run the query has sped up 14.5 times. Now we all know how difficult it is to optimize Q code, and we have spent hours and hours doing it. And this is one of the most significant changes, almost like a paradigm shift in Q that we would observe once the GPU library is fully available. The observed speed up here generally has been 10 to 14x. What this means is that now we can do on-demand intraday rollups, what-if, stress testing, larger feature sets without pre-aggregation, and so on. Uses the familiar QSQL semantics, and we can validate edge cases, and so on. Third example is GPU VWAP. We are using the VWAP formula. It's really here just to show that, just to give a comparison of how fast it can be. So I'm going to run GPU VWAP on CPU, 77 milliseconds. And similar to the prior example, we're going to use the functional form of the same query. So we show the parsed version and we run it on the GPU. That took 18 milliseconds. And if we see the speed up, generally what we have seen here is 4 to 20x to 25x speed up, depending on the query that's being run. What this means is that now we can run VWAP analytics at 4x, 5x, 10x the usual speed. So we can have more symbols and time buckets, but using the same infrastructure and all, but all we are doing is just adding a GPU card so that we can use .gpu.select instead of just select. The last few examples, transaction cost analysis. In this example, we're loading a 20 million trade table and a 200 million code table. The idea here is that can we accelerate on TCA and perform as of joins by performing as of joins on the GPU. In order to do that, we have .gp.aj, and again, like before, we're going to move the data back and forth using .gp.to device and .gp.from device. So just to look at the tables here, 20 million trade, 200 million code table. Um, so we are running it firstly on the CPU. And if you see, here, if we have the formula for AJ, the part that really speeds up is the binary search within the AJ formula, and that makes a significant difference because we are offloading the binary search onto the GPU. So let's now compare the CPU time and the GPU time. 1719 versus 106. The speed up is 16 times. So there's a 16x speed up on AJs. Generally, we have seen this vary from between 4 to 15 and so on. So it does depend on several factors, but size of the data that we're using for VWAP, the capacity, and so on. But given as of joins are already so significantly fast within KDB, what essentially we're showing here is that, again, by a very simple switch from instead of using AJ to switching that to .gpu.aj, we have obtained a 16x speed up in the overall performance. So what this means is, from a business side, we can support now deeper intraday slices. We can use more symbols, longer lookbacks, and essentially lower slippage or impact. Finally, the last couple of examples here, custom kernels. We can use custom kernels from Q to speed up basically proprietary calculations, again, without leaving the .gpu stack. For this, we have a function called .gpu.jit.reg. And I won't be going through this entire thing, but feel free to pause and review some of the operations that are shown here. There's a shift kernel, which just takes an array of numbers, adds a fixed value to each element. There's a simple example that has been shown in order to demonstrate what .gpu.jit.register does. And in this example, we're using .gpu.jit.reg to register a particular function, a fairly complex TCA calculation. And what we're going to do is do 50 as of joins with time shifts. So 0 to 10 to 20 to 490 milliseconds. So basically lags of 0 to 10 milliseconds. We're going to create columns T0 to T49 with mid prices. We're going to do that as of join on the CPU, and then we're going to do the as of join on the GPU. The same 50 as of joins, mind you. What we have seen in these sorts of very real world, very realistic, examples that you would typically find, we have seen speed ups generally in the order of 2 to 3x, but that in and of itself is very significant. We're basically saying that we can halve the time. So as you can see, the CPU operation took 17 seconds, the GPU operation took 8 seconds. So so overall, I think, from the examples we've seen so far with as of joins, it's quite obvious that there's significant potential, but of course, there's a lot of testing that remains. The final example here is to demonstrate the matrix multiplication performance. What we're going to do here is we're going to simulate 1 million OpenAI embedding vectors, that is 1 million vectors of length 1536. We're going to use .gpu.gem in order to multiply a vector with that matrix. Basically, we are simulating a similarity search. So we're going to do the matrix multiplication in the CPU first, using mat$vec, and then we're going to do the same operation in GPU using .gpu.gem. So in other words, what What this means is you can also do vector database operations using using the GPU functionalities or the GPU functions that are going to be available to you via the GPU library. If we do a comparison of the speed up, we see a speed up of 167 times. We have generally seen speed ups here between 150 or 200 to 500x. Um, a significant speed up over the KDB MATMUL MMU. Um, and essentially, it opens up a whole new set of use cases, as I mentioned, with regards to whether it's vector databases or matrix operations, linear algebra, and so on. So this enables bigger cross-sectional transforms, near real-time factor recomputes. You are essentially offloading dense math calculations from the CPU to GPU, and it works at scale. But I suppose one of the most striking thing with all the examples that I've shown so far is that all of these have been run on a GPU card that costs only $1.18 per hour. It's a single A100 card that has been rented for $1.18 per hour. And what this means is that all it took for me to speed up my operations, my KDB Plus operations, my select statements, my as of joins from 5x to 200x is a single GPU card that costs $1 an hour. So from all the examples we have seen, and it's all well and good, right? The technical part is the technical benefits, the technical performance. That part is quite obvious. But what does this mean from business perspective? So for algo testing, before back testing on sample subsets, for intraday strategy reoptimization, you may have nightly offline updates and so on. What the GPU does is that now, instead of using sample subsets, you can backtest on entire tick level market data. What that means is, again, from business outcome perspective, you can run 4 to 5x more strategies in the same window. Your research cycle time goes down significantly. Intraday real-time on-demand reoptimization. So you can adapt to regime shifts faster, capture short-lived alpha, and so on. Similarly for TCA, we can, instead of, recalibration taking, hours, now we can analyze market impact for hundreds of lags. We can do full sweep in seconds. Same day TCA reporting, real-time full order book depth metrics instead of top of book. What that means from a business outcome perspective is that now we can have much better, or at least we can do our analysis to determine venues more optimally. We can expect slippage reduction. We can fix issues in terms of TCA, on time, reduce the outliers, and so on. And finally, in terms of compliance, intraday VAR refresh, earlier breach detection, faster limit management, and faster regulatory reporting. Overall, um, the business value proposition, again, in this case, is quite obvious. So overall, we think that what we have here represents a significant shift in how we have generally worked with KDB Plus. It's a step change in a tick database paradigm. This breakthrough time series performance, full KQ flexibility at GPU speed, multi-GPU parallelism, at-trade decisioning, and overall, all of these have a compounding advantage. And all of these have a very quantifiable business return as well, which is again quite evident. But again, yes, we need to run our tests, our cross validations, whatever we may be doing in order to assess the individual or level benefit in your particular situation. But in general, in a reduced time to market, 4 to 5x more runs in the same window, better execution quality, higher quant productivity, and higher efficiency at lower TCO. So overall, I hope this has been helpful. I think there's a huge potential. We think there's a huge potential here at KX with the GPU libraries. Now, I should add that this is still in the early stages, so there's a lot of work that still remains. But this was just the first, glimpse of what is possible in this with this new GPU library.